Great. Good morning, everyone. Welcome to Research Talks. I would like to start by acknowledging that at the University of Waterloo, much of our work takes place on the traditional territory of the neutral Anishinaabe and Haudenosaunee peoples. Our main campus is situated on the Haldeman Tract, the land promised to the Six Nations, that includes 6 miles on each side of the Grand River. Our active work towards reconciliation takes place across all our campuses through research, through learning and teaching, community building, and it is centralized within our Indigenous Initiatives Office. My name is Charmaine Dean, and I'm the Vice President, Research and International at the University of Waterloo. I'm so pleased to welcome you all this morning to Research Talks about enabling disruptions. And we've just been through major disruptions, and that's continuing, and looking forward to hearing about the next generation of additive manufacturing. At the University of Waterloo, you know that our research is focused on impact on everyone in our community. We want to share our research with you, engage in conversation, hear your questions and thoughts. We believe that society advances best when universities are connected to the community, to industry, to policymakers who are shaping Canada and the world. We do this through research and also through students. You know, we are famous for our co-op program, where students spend time in industry and also spend time in academia in order to have a jump start on the world when they go out into actual employment. This is our third virtual Research Talks event. We moved to virtual, of course, to be able to engage with you through these times. We also recognize the importance of incorporating perspectives from outside of academia as part of our research, and we've been doing that for the last 3 years on our panels. So we're going to hear thoughts through presentations, and we're also available to answer your questions at the end of the session. We are recording this session, and we will post it on our website as we've done with our previous sessions. We start Research Talks with a brief description of each of the speakers in the panel, and I'll be pleased to present you each of our speakers today. Then each speaker will be delivering a short presentation about their work, and then at the end we'll take questions from the audience. And I invite you at that point to put your questions into the chat line. If you're directing your questions to a particular panelist, let me know that when you send your question through the chat line. And if it's a general question that could be directed to all the panelists, then we will make sure that a variety of speakers have the opportunity to weigh in on the answer to your question. So I'll start with the panelists who are presenting today. And as I mentioned the panelists, Devian, it'd be nice to focus attention on them. We start with Essam Toyser-Kearney, a professor in mechanical and mechatronics engineering. Essam holds the Canada Research Chair in Additive Manufacturing. He has over 20 years experience in different aspects of additive manufacturing research and development, mechatronics, AI system development, applications in medicine and engineering. He established the first additive manufacturing laboratory at a Canadian university, the Multiscale Additive Manufacturing Laboratory, focusing on the development of next generation of additive manufacturing processes and applications. A lot of work in Essam's lab is on applications and supporting our industry and government partners. His lab is now the most comprehensive academic facility in Canada, and it's one of the world's top 5 academic additive manufacturing facilities. He is an active steward in this field, a lot of leadership from Essam's lab, for this field globally. He's a member of the American Society for Testing and Materials International Committee. It's a leading committee in the development of standards for additive manufacturing. He's also a member of the Additive Manufacturing Advisory Committee on Advanced Manufacturing Supercluster, and he was a member of the NSERC Selection Committee for Strategic Grant Applications in the advanced manufacturing area from 2015 to 2018. He's a recipient of so many invited talks in so many different countries. I won't list many of them, but I will let you know that he's also been doing a lot of work on commercialization and has published 125 related additive manufacturing journal articles. His research has been recognized through many awards and honors. Such a pleasure to have you here with us, Essam. Mahalia is an assistant professor at the University of Waterloo, also in mechanical and mechatronics engineering. She's the research co-director of the Multiscale Additive Manufacturing Lab. Her research focuses on innovative design and process optimization, as well as the adoption of new materials for powder bed fusion and powder bed binder jetting additive manufacturing processes. Her research goals are to bridge technology gaps that are necessary for improvement of part quality, for the repeatability of processes and reliability. And of course, this is really important in moving from research prototype development to actually large-scale manufacturing. To tackle these challenges, she collaborates closely with many industry partners in the additive manufacturing supply chain and in applications domain. Thank you very much, Mahalia, and we're really looking forward to your presentation. Ali Bondakar works at Siemens Energy Canada Limited. He is an advanced manufacturing technology lead responsible for strategic development of various advanced manufacturing processes, with obviously a particular focus on additive manufacturing. In addition to his industrial role, he's also an adjunct professor at Concordia University, the University of Waterloo, and he leads several industrial academic research projects. He has more than 20 years of industrial and academic experience in different aspects of mechanical engineering and advanced manufacturing, gas turbine engines. He works at the world-class aerospace and energy industries, for example, at Rolls-Royce and his current employment. He completed a PhD in mechanical engineering in the Department of Mechanical and Industrial Engineering at Concordia, and then he continued his studies as a postdoctoral fellow at the Center for Intelligent Machines at McGill University. He has published patents in metal and additive manufacturing. He's a co-author and an author of 35 scientific publications, and most of his publications are in advanced manufacturing and materials. Ali, a real pleasure to have you here today. Melissa Dapri is a program leader, metal manufacturing and systems within NRC. As you know, we have a strong collaboration with NRC, and very happy to have Melissa here as part of our panel today. She's a manager in technological innovation, experienced in the establishment of industrial collaborations and research and development in metallurgical materials and processes. She has over 20 years experience in aeronautics, in automotive and surface transportation, and in health technology sectors as well. She has significant professional achievements, including lots of work related to professional societies and in the industrial sector in advanced manufacturing. She combines technical expertise and managerial and relation skills to manage very large-scale research and development programs and projects. She is known at NRC as a visionary and a very organized person because of the ability to mobilize these large-scale processes to achieve results. Within the Automotive and Surface Transportation Research Center, Melissa provides leadership in advanced manufacturing technologies for mass customization, advanced mechatronic platforms for incremental manufacturing, manufacturing technologies for lightweight applications, surface engineering for advanced manufacturing and for harsh environment applications, corrosion and durability in a multi-material context, and smart tooling. She sponsors 2 large industrial R&D groups and will probably let us know about those today. I'd like to welcome all our 4 speakers, Essam, Mahalia, Ali, and Melissa. Thank you very much for coming to Research Talks, coming to the University of Waterloo, Melissa, and taking time from your schedules to join us here today. First, I'd like to invite Essam to tell us about his research. Thank you very much, Essam, and Divian will move to Essam's presentation.
I'd like to thank Professor Charmandine for the nice introduction. Also, I would like to thank you all for participating in this research talk. Let me start with this slide. Additive manufacturing, known as 3D printing, works based on a layer-by-layer fabrication. It takes a digitized model, then after some special pre-processing for converting the digitized model to slices, the process data is fed into the additive manufacturing machine. Depending on materials and applications, one of 7 classes of additive manufacturing can be selected. After this step, there might be some requirements for cleaning and heat treatment to arrive at fully functional parts that can be from metals, composite, or polymers. As seen in this chart, the process enables the fabrication of complex parts so rapidly, thus enabling to move from art to physical part directly. For clarification, additive manufacturing is not one process. According to ASTM standards, AM includes 7 processes. The most common one is material extrusion, known as FDM, and very popular for printing plastic parts. The 3D printers used at homes and offices are mainly from this type. However, among more comprehensive and challenging processes, there are 3 that are used mainly for metal additive manufacturing: binder jetting, powder bed fusions, and directed energy deposition. Here at the University of Waterloo, we are mainly deploying these technologies for innovative R&D with industry. As the modern history of AM is almost 35 years old, the versatile technologies and broad materials motivated people to adopt this technology for different applications. Back in 1995, the technology was mainly used for rapid prototyping, for design verification and visualization. The technology has been used for rapid tooling and casting, in which the prototype parts were used to develop molds and cast. In the first decade of new century, the AM technologies started to be used in the aerospace and automotive industry to make customized polymeric parts as jig and fixtures. In the second decade of new century, the technology was commercialized for dental and orthopedic applications. That is a very, very growing market for additive manufacturing. The technology has been commercialized for the jewelry and cloth industry, the film industry, as well as aerospace for metallic parts. And there are emerging applications of the technology in other industries like food, non-planar electronics, building, and biodegradable implants. And in future, we will hear more about full organ printing and in situ biofabrication. Public interest have been dramatically increased. Look at this Google trend. After this chart from Google Trend, after 2013, the public interest has been increased more than 40 times. And that time was associated with the news associated with printing guns and also endorsement of President Obama. Market size is also booming. The market size was $14 billion in 2020. This is the fastest growth among any manufacturing industries. The annual growth rate is more than 20%. But why? But why additive manufacturing? There are many reasons for this high level of interest among industry, public, and academia. The reasons can be classified into three categories. From my perspective, technical and cost-saving benefits, health and humanitarian impact benefits, and environmental and societal benefits can be, in fact, those categories. One of the major applications of additive manufacturing is prototyping. Such prototyping usually carries at a fraction of cost compared to other conventional processes and at usually non-disputable speeds. This rapid turnaround usually accelerates the production development cycle that includes design, test, revision, and redesign. Products such as molds that could require more than 6 months to be developed by conventional methods can be ready for operation in 2 months if being made by additive manufacturing. As seen in this chart, on-demand manufacturing can be realized so effectively and so rapidly by additive manufacturing. AM enables the fabrication of complex shapes that cannot be produced by any other conventional methods. The additive nature of AM offers an opportunity where geometrical complexities will not come at a higher price. Opposite to conventional methods, AM offers a platform so-called design for use rather than design for manufacture. It should be noted that parts with organic geometry normally perform better. This feature of AM will enable to design beyond imagination and provide tools for more creativity, flexibility, and efficiency. Parts consolidations and lightweighting are the major benefits of additive manufacturing from my perspective. There is a major trend among manufacturers to fabricate both greener and more economical products, a serious obligations towards environmental sustainability has forced industry to develop lightweight components where AM is a key player for this goal. In complex mechanical machines, there are more than tens, hundreds, or even thousands of components that are either welded, bolted, or press-fit to each other. Parts consolidations offer many advantages due to the reduction of number of individual parts needed to be designed, manufactured, and assembled to form the final system. There are many advantages that I can actually talk about them for hours, but just to name one. Parts consolidation reduces overall risk of a system, where the number of risks associated with too many suppliers of individual parts drops. Take a look at this figure, take a look at this photo, and I believe this photo says 1,000 words. This is a CT-7 engine midframe that is used in helicopters. 300 individual parts have been consolidated in one printed parts. 7 assemblies have been converted to one, and 10-pound weight reduction has been resulted. Just for your information, AM parts can bring weight reduction in the range of about 50 to 100 kilograms per jet engine. This will result in a significant reduction in fuel costs. Each pound reduction from every aircraft in a fleet of 400 commercial jetliners like Air Canada annually reduces fuel consumption by 30,000 liters. Just a few more examples that benefited substantially from lightweight and part consolidations. Here you can see 3D printed rocket engine and antenna, both used in the aerospace applications. The space travel programs and NASA have substantially benefited from additive manufacturing. SpaceX has been using AM increasingly in its production to optimize processes and produce parts that are not possible with conventional manufacturing method. Given the fact that SpaceX is a champion of vertical integration, meaning that they bring in raw material at one end and a fully manufactured rocket comes out of the other end of the factory, AM is the tool on the hand of SpaceX. The integration of multiple advanced materials and sensors into one component is one of the most rapidly developing areas of additive manufacturing. Cellular and lattice structures with embedded sensors are now becoming a main research thrust in many R&D centers. Look at these two parts developed at the University of Waterloo. At the left, a smart tool with embedded fiber optic sensors that can measure force nearby the cutting edge. The other one is flexible sensors composed of graphene and silicon for wearable devices used in measuring forces. These innovative products cannot be made with any other techniques. And parts repair, refurbishment, and solid freeform fabrication are among other benefits of additive manufacturing. Machining errors or last-minute engineering changes can affect on-time delivery of tooling and impact the kickoff date of new products. AM can be applied as a safe technology to repair tooling, especially on critical contacting surfaces. AM, in many cases, can save high-value components that would otherwise need to be replaced. As seen, AM has been used in situ repair and freeform fabrication of features on previously fabricated parts by other methods. It can also be used for making legacy parts where the supply chain is not available anymore. AM offers a simpler supply chain. The recent pandemic has changed the mindset of governments, and they are now incentivizing local manufacturing to boost not only local communities, but also be ready for future crises. AM will play an important role in the realization of local manufacturing. In addition, more innovators and user entrepreneurs are turning into on-demand manufacturers, utilizing the opportunities of access to flexible local production. A shift towards local manufacturing has already begun. Interruption to the global supply chain during crisis can be catastrophic to the health and well-being of society. AM processes can provide remedies during such crises. In March 2020, exactly last year this time, the 3D printing community got together to help in making medical devices during a very hectic period when medical centers were suffering from lack of PPE. In the Waterloo region, the 3D printing community got together and coordinated by a local company called Inksmith. In a short period of time, more than 200,000 face shields were made and donated to hospitals until the global supply chain started to provide supplies again. I'm very proud that the team at Essam contributed to this goal significantly. Given the history and this story, the same distributed fabrication model can be used in any crisis, but it surely needs some proactive planning by the governments. The biomedical sector has been benefiting from additive manufacturing for almost 15 years. Customized prosthetic and implants are already being manufactured by AM. As seen in this slide, many innovative customized implants have been developed for different applications. Alongside the obvious benefits to industry and medicine, AM is explored as a potential aid to humanitarian issues. Intensive R&D is already taking place in 3D printed houses to assist in the provision of homes and shelters in regions of need. In addition to undisputable process flexibility and benefits, AM also offers several major environmental benefits. If the process chain and designs are properly developed, AM technologies are usually greener than conventional methods because there is less material wasted and less steps required to fabricate the parts. However, a full cycle assessment must be conducted on the AM part to ensure its design is fully optimized for additive manufacturing. The plot shows in this slide is very interesting. It shows that if we use AM for conventional design, the CO2 emissions even increases. But if we do a comprehensive design for AM, followed by life cycle assessment, the CO2 emission drops by more than 50%. This is one of the main motivation factors for industry to adopt AM for their business sustainability. Like all innovative and emerging technologies, challenges exist for AM. However, these challenges have brought many opportunities for industry, academia, and public. Shortage of qualified materials for AM has brought many opportunities to develop new alloys with superior performance. Speed and productivity issues have brought to the market many innovative AM systems with multiple lasers and automated powder delivery systems. Repeatability issues and in-situ quality assurance have motivated companies and universities to work massively on innovative integrated AM and artificial intelligence platforms. Lack of industry-wide standards have mobilized many standard organizations like ASTM and ISO to work together and develop effective standards for additive manufacturing. Issues with end-to-end workflow, integration, and automation have encouraged companies to work on new software and AI algorithms. Interestingly, AM additive manufacturing has the highest adoption rate of artificial intelligence among industrial manufacturing platforms. Software limitations have encouraged companies to add AM process constraints to modeling and simulation packages. Security issues when hackers may add intentional defects in parts being printed that may cause catastrophic consequences have created an opportunity to develop new firewall for process and supply chain. And skill sets gap has created a lot of opportunities for engagement of academic through the development of new curriculums and certification programs. And it is happening in many major universities like MIT, Carnegie Mellon, and many high caliber European universities, and here at the University of Waterloo. And let me just finish with this slide. This is a quote from Richard Davini, a columnist at Forbes. He says, today additive manufacturing is achieving economies of scale in a variety of ways and doing so without sacrificing economics of scope. No longer limited to product prototypes, customized one-offs, or specialized items made in small quantities, AM is now beginning to take over the kinds of mass manufacturing that have long dominated the industrial economy. Ladies and gentlemen, additive manufacturing is a long-term game changer. Thank you very much for your attention.
Fabulous presentation. Thank you so much. I really appreciate the sustainability angle that you've also presented here. We'll come back to you at the end with questions from the audience. Let's move to the CoLab director, Mahalia. Look forward to your presentation now. And Divian, thank you, Divian.
Well, good afternoon, and thank you so much for your kind introduction. It is my pleasure to introduce brief highlights of R&D efforts spearheaded at the Essam lab to address technology gaps, specifically in industrialization of additive manufacturing processes via innovative approaches in design, process modeling and optimization, and adoption of new materials. I'm extremely lucky to be working with some of the most talented research here at the Essam lab, where we leverage the largest metal additive manufacturing academic research facilities in Canada. And we do so to engage not only in scientific discovery and industrial R&D, spanning across multiple sectors, but also to engage in education and training. In our day-to-day, we work on solving some interesting challenges in the field of additive manufacturing. The first challenge is to tackle the adoption of new materials for AM processes, specifically metals, which can enable new supply chains and market sector opportunities. The second challenge is to work on the next generation of machines and custom manufacturing systems, either for research discovery or in partnership with industry. The third challenge is to leverage data science, modeling, and simulation towards improving the digital tools in additive manufacturing. To achieve these goals, our work spans the majority of metal additive manufacturing technologies, as shown on the right, with a secondary focus on ceramics and polymers as well. To better understand the competitive advantages of additive manufacturing, let's take a look at the way shaping of materials takes place. The shaping of materials into objects within manufacturing processes can be achieved by one or a combination of three basic principles. Subtractive and formative shaping, as described here, are considered to be conventional manufacturing approaches. Additive manufacturing, unlike subtractive and formative shaping, is the process of fusing units of materials together at select locations, usually layer upon layer based on digital designs. Components manufactured using these three approaches can be combined into more complex shaped products by a variety of different joining processes. This process of fusing units of materials together is what makes additive manufacturing unique. This means that you can generate architected materials at the micro, meso, and macro scale. At the micro scale, one may influence the material properties by tuning each unit of material to a unique chemistry or material property. At the mesoscale, one may influence functional properties via cellular architecture designs, such as lattices. And of course, at the macro level, as Essam mentioned, we have new design freedoms which are not available via other conventional manufacturing technologies. Although known under many different names, I will be using additive manufacturing, or AM, throughout the presentation to describe this class of technologies. AM processes, as Essam mentioned, have been around for quite some time. It was only recently that the consumer and industrial markets have seen accelerated technology adoption in this field. This is because most of the original patents on the 7 classes of additive manufacturing technologies, 7 core classes, have expired in the last decade. Since then, the market has become more competitive, with vendors offering either more technologically advanced systems or lower cost options. I'm showing here the so-called 7AM classes along with the timeline of their invention. These technologies have evolved since then to accommodate for multiple materials to be adopted under the same technology class. As well, new technology classes have also emerged. Today, I will only focus on laser powder bed fusion. In the metals domain in particular, we see a boom in technology uptake and industrialization. This is mainly driven by, as Essam mentioned in the past, increased number of alternate technologies that can address metal production, proven competitive advantage of design freedoms in innovative products, as well as an increased comfort level with AM tech based on proven part life cycles across multiple sectors. Barriers still remain. There is a perceived risk due to high initial capital costs and the R&D nature of these technologies. There is still a need to increase material libraries for these processes as well. In addition, there is a recognized talent gap and software tools gap to effectively deploy AM. Now let's take a look at how we address these gaps at the Essam lab. Although we focus on multiple metal additive manufacturing technologies, I have selected only one process to cover today, called laser powder bed fusion. In this process, thin layers of powder with a layer thickness smaller than a human hair are spread and selectively molten at specific locations within each layer using a very fine laser beam spot. The sequence is continued until the parts are completed. This is a thermal process which requires support structures not only to anchor the part to the build plate, but also to ensure heat transfer, reduce part curling, and reduce porosity defects. For laser powder bed fusion, the laser material interaction is in essence a micro-welding process, where the material undergoes melting, vaporization, and often ejection. With each added layer, the material is exposed to melting, solidification, and thermal cycling, influencing the microstructure and material properties of the final component. The process, believe it or not, has more than 100 parameters that can be tuned in manufacturing. In addition, these parameters are sensitive to the design geometries being printed and can result in part failure if not selected properly. This is why at Essam we are working on research that de-risks material adoption and increases process robustness. These goals are achieved by research efforts in process modeling and simulation to predict the behavior of the laser material interaction and to narrow in onto optimized process parameters that result in successful products, even when printing challenging geometries. In addition, we work on sensor data analytics to monitor the process and to eventually react to perturbations via control schemes. In addition, our lab is exploring new material systems in laser powder bed fusion and other technologies in collaboration with industry partners to address technology adoption in numerous sectors. This is an illustration of the typical scales of customization in laser powder bed fusion that, when combined, can influence the final behavior of the product. At the microscale, one may influence the microstructural properties, part density, and surface topography of parts. At the mesoscale, one may influence functional properties via cellular designs such as lattices. And of course, at the macro level, we have new design freedoms which are not available via other manufacturing techniques, as can be seen here in the surgical tool instrument. To accomplish customization at these three different scales, at the Essam lab, we look at the process chain holistically from powder to product, to find process parameters that result in repeatable components. And we achieve this by looking at low-cost powders or new powder material systems, and we try to understand their properties. Following this step, we strive to refine and deploy complex process modeling, statistical designs of experiment, or data science approaches such as machine learning to optimize process parameters at low cost. Once process parameters are optimized, samples are manufactured and characterized to quantify their quality. Let's take a look at a few examples of modeling to achieve parameter optimization. In laser powder bed fusion, we are working with a very small laser beam spot. At this scale, materials can experience melting or even boiling and vaporization, depending on parameters used. Here we can see examples of how materials behave in boiling at the top, in transition or conduction with minimum defects in the middle, and in an undermelt condition as shown at the bottom in the CT scans of the objects shown. All these regions will have different mechanical properties and material properties. Furthermore, we can model these melt pool morphologies to be able to stitch weld lines together to create low defect parts. For some instances, statistical models can be deployed for creating process maps and for optimization of process parameters. These approaches are quite powerful, but do rely on a larger set of experimental points to inform a model. Similarly, machine learning models are a new area that is being explored. Using this approach, multiple data sets are used to train and test models as well. Such data sets can be informed by process inputs, sensor data, product qualities, or physics-based models. This is really an exciting field with significant work ahead. Now, in the last couple of minutes, I'd like to take a look at how we deploy laser powder bed fusion to solve real-life problems via two examples. In this case study, Intelligent Surgical came to us with an interesting problem. The group uses a surgical tracker and a camera system to assist in the alignment of an acetabular cup in hip replacement surgeries. Specifically, the surgical tracker, as shown here on the right, was a challenging piece to manufacture using conventional manufacturing techniques, requiring a complete rethinking of the design space. In developing a solution, researchers at the Essam lab first selected and characterized a titanium alloy suitable for this biomedical application. Then we proceeded with multi-scale simulations to be able to tune process parameters for manufacturability of challenging designs. And furthermore, we lightweighted the design via topology optimization with care to manufacturability, ergonomics, and part functionality. We then simulated the manufacturing process and produced the final parts. One of the most important lessons really has been that innovative thinking in additive manufacturing as well as machining have to go hand in hand to produce a technically sound and economically feasible product. And in my last example, the researchers at the Essam lab and the QPL lab here at the University of Waterloo looked into the feasibility of deploying laser powder bed fusion for the fabrication of optical device components, such as interferometer housing and adjustable mirror holders. This assembly is envisioned to be suitable for novel advanced communication systems. The team worked on adopting a new nickel-based alloy with a high thermal stability. In addition, we explored the design space towards producing this innovative interferometer. The complex design space required our team to deploy modeling and simulation, as well as statistical designs of experiment to optimize our process parameters. One of the most important lessons that we learned has been that it is often challenging to really fully utilize one's imagination to be able to leverage the true design potentials in laser powder bed fusion. For instance, on the left, we started with a design concept that was rooted in conventional manufacturing. This continuously failed in the laser powder bed fusion manufacturing step. As soon as we started to think out of the box, this is when we finally were able to manufacture the entire optical assembly successfully. To find out more about exciting projects, please don't hesitate to contact our team. Thank you so much, and now back to you, Charmaine.
Thank you so much, Mahalia. Love the applications, especially on the medical side. Thanks for bringing that to us. Divian, we'll turn the attention now to Ali.
So hello, everyone. I presume you can hear me well and see my presentation as well.
Yes, we can, Ali.
Okay, great. Thank you very much for the introduction. And I'm very happy that I have the opportunity to talk about additive manufacturing research at Siemens Energy briefly. So I'll start with a couple of words regarding Siemens Energy, who we are and what we are doing. And then I'll continue with the giving you a perspective, an overview regarding Siemens Energy additive manufacturing capabilities, and then I'll finish with a couple of words regarding our additive manufacturing research activities. At Siemens Energy, we have 88,000 people, employees working in 5 different divisions: oil and gas, industry, power generation, renewables, transmission, and new energy business. In oil and gas, we're making mostly gas turbine engines with applications in oil and gas transmission. In power generation, we're making heavy-duty gas turbines and steam turbines and generators. Renewables are centered around the wind turbines, and new energy business consists of hydrogen and energy storage. So in the gas turbine industry, we have extensive portfolio and our engines can generate power from 4 megawatts up to almost 600 megawatts. We have 3 classes of gas turbines: aeroderivative gas turbines, industrial gas turbines, and heavy-duty gas turbines. Aeroderivative and industrial gas turbines are mostly used for offshore and inshore applications for oil and gas industries. Heavy duty for power generation, electricity. I belong to aeroderivative gas turbine industry. We have a center in Montreal, more than 400 people working here, and more than 200 people are fully involved in research and development. I presume you can imagine how extensive could be our research and development activities. Particularly for advanced manufacturing, we have focused on additive manufacturing, low emission combustors, advanced machining, advanced combustors and turbine designs, manufacturing simulation, general digitalization, higher temperature materials and coating, HVOF, plasma spray, laser electron beam technologies, mostly for welding and joining. Particularly for additive manufacturing, which is the topic of the conversation today, we believe that this is a game changer technology, and there are lots of benefits associated with this technology, including time to market lead time reduction through fast technology validation and shorten the process development, supply chain and reduce complexity, mitigating the single source, and also reduction of the assemblies to one component. For instance, we have different components consist of different manufacturing processes, and we can consolidate all in just one process, which is additive manufacturing, that can lead to cost saving, cost reduction, which is one of the main motivation for industries to acquiring this technology and developing this technology. Environmental benefits by reducing the emissions through the complex designs, through the enhancement of the design, and also innovative designs by new geometries, more complex design, and using different physical phenomena for the design, like for instance, negative Poisson ratio, negative stiffness for lattice structures. In terms of the capability available, the machines and hardware, we have 2 centers for repair and serial production. One in Finspång, Sweden. We have about 15 additive manufacturing machines installed there, with a focus on repair and serial production. This center in Sweden is mostly used for parts and components from Siemens Energy. And the other one, which is based in UK, Material Solutions, is service provider not only to the Siemens components, but also for the other industries as well. 19 additive manufacturing machines are there, and the plan is to increase to 50 machines. Both of them are new state-of-art additive manufacturing facility, and there are lots of capabilities, and the plan is to expand them in the next couple of years. In terms of the components that we have developed and designed and printed, we have more than 150,000 hours engine experience for Siemens parts, for gas turbine, mostly for gas turbine engines. There's just on the right side, there are just a couple of new just examples of the components: burner head for serial production, for spare parts, and all. The last one is the turbine blade, stage 1 for the Siemens gas turbine, which is SGT 400 engine. 75% technology validation, which is very difficult to validate for the rotating parts, but we've achieved the milestone so far. In addition to the Siemens components, we have printed several components for aerospace industry and automotive, for aerospace, nickel-based superalloys, different lightweight materials, structural parts, and advanced combustion designs for them as well. We are printing parts, and also at the same time we have the capability for designing of the parts. So we have the full capability from the design to manufacturing and post-processing. And for the automotive, titanium materials and higher strength materials as well. For the capabilities in terms of the material, we have qualified different materials ranging from the nickel-based superalloys to cobalt, non-weldable, weldable, and also qualified materials for external applications, which means or customers in automotive industry or aerospace industry. All in all, I can say that Siemens is one of the largest additive manufacturing Siemens has one of the largest additive manufacturing fleets in the world, and we are leading this technology, we're developing this technology. In addition to all these things, we have invested significantly in research for technology development from TRL 1 to 4 for the basic research or fundamental research, 4 to 6 for prototyping and validation of technology, and 6 to 9 for pre-production and production. Specifically for the research, we have been focusing on different areas, including materials and process. For process development of the technology, it's not only for the selective laser melting or powder bed fusion. It can be binder jet or FDM or other applications as well, other technologies as well. Material development, multi-materials, new materials, digitalization and automation, digital twin of the product, digital twin of the production and process as well. Data acquisition for handling to enable the machine learning, which is a subset of the artificial intelligence. Design for additive, extensive research internally and externally for design for additive, multi-physics topology optimization, lattice structures, the physical concepts like negative photon ratio, negative stiffness for the enhancement of the performance of our components. For machining and manufacturing, hybrid additive manufacturing process, post-processing, lots of research are ongoing on the post-processing of the additively manufactured part. Specifically for selective laser melting or laser powder bed fusion, this slide, This slide shows the fully integrated additive manufacturing production line, and at the same time, it shows the area of focus, the areas of our focus in research, from design on the left side, design and simulation of the components, the powder characterization and tailoring the powders, and then process optimization specifically for laser powder bed fusion here, and also powder and handling, the powdering of the complex structures, heat treatment, advanced robotic, multiple monitoring and monitoring of the whole process, and also digital twin, as I mentioned, big data. Separation of the supported structures from part, machining and post-processing, surface finishing. We have research program and different projects for any individual boxes you see here in this slide, either internally or externally. We have in collaboration with different universities across the globe, in Europe, in United States, and in Canada. Specifically in Canada, we signed an agreement with the University of Waterloo, Essam, in 2017 for conducting research in 5 different areas: process optimization, process thermomechanical simulation, topology optimization, material simulation, and process monitoring. After 4 years, I would say that it went very well. We met all the objectives, resulted in very good, let's say, outcomes. It resulted in several patents, very high quality journal papers, and we are planning to commercialize a few of them. And I would like to finish my presentation with just one of the examples of one of the outcomes, which is the process optimization, which was patented 3 years ago, filed for patent 3 years ago, and now is available to the public. On the left side, it shows the process. There are lots of science behind it, but I just for the simplification of the process, I put this together to show that it consists of a lot of steps, identifying the key process parameters, and then by the previous training phase, and then after that, determining the most important process parameters, and then optimize them. This optimization is designed to optimize the process parameters for any specific mechanical property, for any targeted mechanical properties. So it means, let's say, for instance, you would like to maximizing the density and minimizing the surface roughness. Then you can use this methodology to come up with the most important, most significant process parameters and then optimize them. On the right side, this is just an example for the Hastelloy X, which we are using in our hot section combustion area. The objective was to maximizing density, maximizing hardness, and minimizing surface roughness. We use this methodology and then come up with the most significant process parameters, and then run the optimization methodology, and then optimize the process parameters, validate it, use it, and validate it on the artifact, and then on the real part, the job done. So this process optimization methodology can be used for any materials and any additive manufacturing processes. So with this, I would like to conclude my presentation, and thank you very much for your attention.
Thank you very much, Ali. And our last presenter is Melissa.
Let me share my screen. Are you seeing correctly the presentation?
Thank you, Melissa. Yes, we are.
Okay, thank you. Oh, hello, everyone. It's a great pleasure to participate in this research talk today. I'm going to talk about a subject that is very close to my heart and that has always been the common thread of my career for the last 20 years, collaboration. So without further delay, I'll dive into the heart of my presentation and present the outcomes and benefit of large-scale collaboration for Canada and how the National Research Council of Canada is working to develop successful collaboration. So I will begin this presentation by saying a few words about the National Research Council of Canada. NRC is the Government of Canada's largest research and development organization with over 100 years of experience. NRC has state-of-the-art research facilities and administrative offices from coast to coast and beyond, with an international presence in Germany and Japan. What do we bring to Canada? Well, through the work of our senior researchers, we advance scientific and technical knowledge in a variety of areas, support the Canadian government's policy objective, and through our industrial technology advisor, we support business innovation. In a few numbers, we have more than 2,000 scientists, engineers, technicians, other specialists, and 255 IRAP industrial technology advisors. We have specialized facilities in 179 buildings and on 22 sites. We drive in a year about 1,500 R&D collaboration and help more than 8,000 SMEs. In 1 year, what does that mean? It means 1,000 publications, 200 patents, $193 million of NRC revenue. Now that you know a little bit more about NRC, I'm going to show you how we create links, how we interact with the different players in the Canadian industry. In order to have fruitful and value-generating collaboration, it's important to be able to bring together the main actors of a sometimes complex ecosystem. Several players must work in synergy. In this more technology push nor technology pull, there is only a consultation of the actors, multiplying the innovation step change and speeding up the development loop. But for this to happen, the actors must feel confident, putting aside the hierarchical notion of their own position in the industry food chain. All actors in this ecosystem are equal, no big nor small company, no global versus local company. It is in this context that we believe that the NRC is an essential player in a multitude of ecosystems. Why? The NRC is recognized as a neutral, unbiased connector and convener. Being public servant is at the heart of our employee. With over 100 years of operation, we have a vast network to draw upon. We connect Canadian innovators to leading R&D capabilities. We enable cross-sector partnership and collaboration in Canada and abroad. We conduct research and we support our SME to help them scale up and compete. In the following slides, of my presentation, I will show you how we concretely go about becoming a key player in relevant ecosystem. I will present you the example of an industrial R&D group that we created more than 10 years ago. The group is called Metaltech, and it's known to be the largest ecosystem led by NRC. Metaltech is a group of companies, not-for-profit organization, and industrial association that work together to bridge the gap between early-stage R&D and technology market readiness to decrease investment risk, to solve industry-wide technology problems, to increase cost-effectiveness of emerging products, to create complex multidisciplinary technological solutions that address emerging industry needs, and to act as a pre-competitive research cluster driving collaboration for the transportation equipment manufacturing ecosystem. More precisely, Metaltech is a community of interest that supports technological innovation in the manufacturing of metal products to increase speed, agility, and adaptability of their production, to create smarter processes for smarter products, and this in the respect of our dear planet Earth. Our member companies and partner cover the entire value chain and work together on the biggest issues in the sector. The main benefit of joining Metaltech is to share the benefits, risk, and costs associated with pre-competitive research. With a minimum contribution, we talk here about 16,000 a year, an individual company with the force of the group can raise up to 3.5 million in research and development activities. Metaltech currently has 27 companies and hope to reach a critical mass of 50 companies in the coming months. So it goes without saying that we are looking for new companies interested in joining the group and benefiting from our research results. Of course, the group counts on the support of more than 10 sponsors and more than 10 academic collaborators, college and university included. Since a picture is worth 1,000 words, see our big brains working together here across the value chain, from raw material supplier to final product. We see all the big names in the transportation industry, either with a Canadian presence or a global presence. The group owes part of its success to its financial partner and academic collaborator. Here we see major private sponsors such as Rio Tinto. We see the provincial funding agencies. We see industrial associations such as Alu Quebec and Aluminium Valley Society. Academic collaborator, many universities across Canada, Quebec University, and soon University of Waterloo. We're about to concretize a new collaboration. And of course, Government of Canada and Government of Quebec work hand in hand to support this group. So at a glance, company, afford a 4 years contribution, $63,000, raise about 3.5 million worth of R&D project a year. There is call for project proposal twice a year, 2 annual member meeting where we conduct R&D steering committee, software user meeting, conference, and emerging technology teaser. We deliver results on a monthly basis through technical webinar. The members get the IP assets through confidential results and non-exclusive licenses. And of course, NRC takes care of the IP protection cost and filing. At the end, it's also a very excellent networking opportunity for the participant. You will probably recall that I mentioned our presence across the country earlier. So Metaltech group members have access to all this expertise like, let's say, a buffet. All they have to do is tell us the problem they face, and we develop a generic scientific program that addresses them by drawing on the expertise of over 250 researchers If we don't have the expertise at NRC, we look for the best academic collaborator to complement the NRC expertise. Metaltech is truly a connector hub that delivers between 5 to 10 major projects per year, each project tailored to maximize the return on investment. We take care of leveraging your investment, finding collaborators, sharing research results, and managing the IP for our company members. Why am I talking about Metaltech today in a research talk entitled Enabling Disruption, the Next Generation of Additive Manufacturing? Well, let me explain further without further delay. The research area of Metaltech are the following. Sorry. Advanced sensing system, data engineering and analytics applied to manufacturing process, high fidelity modeling, simulation, and optimization of manufacturing process, intelligent tooling, corrosion and durability in multi-material context, surface engineering for advanced manufacturing, manufacturing for structural lightweighting application, advanced mechatronic platform for incremental manufacturing, and additive manufacturing for mass customization. So you may be wondering about NRC's capabilities in additive manufacturing. Well, this image illustrates just how extensive they are. We have TED laser blonde powder, high fidelity simulation, hybrid laser powder bed. We have robotized additive friction stir welding, mesh-free modeling of additive friction stir welding, wire additive manufacturing, cold spray additive manufacturing, high fidelity simulation of the AM process, or various AM process, I should say. Feedstock powder feedstock development, printed electronic, powder manufacturing, and soon in our new site in Winnipeg, high temperature laser powder bed, binder jet, and CPPS additive manufacturing. And what does NRC do with all these great expertise and amazing equipment? Project, of course. So in the following slide, let me show you a few projects conducted in 2021 in Metaltech. I told you earlier that NRC and Waterloo University is about to start a new collaboration on additively manufactured die casting tool in life. Here it is. So the objective of this project is to compare the life to failure of laboratory scale additively manufactured, conformally cooled specimen in a representative environment. Identify design and laser powder bed fusion parameter to increase the life of additively manufactured inserts and therefore reduce process and maintenance costs. The expected benefit and impact for the industry member are to provide design and laser powder bed fusion process parameters favoring longer die casting insert life, therefore reducing process costs per part and increasing competitiveness. The compromise between deposition rate and material property, as well as between cooling capacity and expected life, will be highlighted. Thermal testing will also provide a comparison of the expected service life for different process parameters, design, and/or material, compared to conventional H13 steel as a reference. The second project is entitled Manufacturing Process Simulation of Laser Powder Bed Additive Manufacturing. The objective of this project is to develop state-of-the-art computational simulation platform and multi-scale laser powder bed fusion model. Develop a numerical model to optimize support structures based on process simulation. The expected benefit and impact for industry is to reduce the cost of developing new part by 50% when compared with the expensive experimental trials, and help Metaltech members to increase their competitiveness in the field of additive manufacturing fabrication and to accelerate the adoption of the LPBF process. The third project is the optimization of thermal management of the tool used for aluminum forming with additive manufacturing. So the objective of this project is to develop a software platform or a workflow based on the topology optimization in company with a new composite powder for LPBF to optimize thermal management of tools in aluminum forming industry. Expected benefit and impact for the industry is to deliver an efficient and uniform heat treatment transfer in mold and part, reduction in cycle time, and lower mold and in stress, which result in better, of course, mechanical property, less warpage, reduced rejects, and less risk of recall. At a larger scale now, we develop an incremental manufacturing platform for structural aluminum. So the objective of this project is to develop a robotized incremental manufacturing platform combining cold spray machining, featuring unique capability for producing vehicle-scale 3D structure in high-strength aluminum alloy. The expected benefit and impact for the industry is, we anticipate that with this first of its kind incremental manufacturing platform, we could drive lightweighting as much as 10 to 25% reduction through enabling topology optimized additive manufacturing of vehicle component and or fabrication of tailored blanks. The fifth project, die-less forming of complex sheet metal component. This is additive manufacturing, or maybe more prototyping or 3D prototyping of the of a sheet metal. So the objective of this project is to develop B-Robot ISF technology that is cheaper and more flexible than what is currently available on the market. The expected benefit and impact for the industry is to produce parts without matrices quickly and at a fraction of the actual cost directly from CAD. And the last project under development right now is on binder jet for structural aluminum component. So the objective would be to develop aluminum powder feedstock, binder, and printing process parameter for structural aluminum components typical of transportation industry. Develop post-processing steps, curing, depowdering, debinding, and sintering parameters optimization of those printed parts. And with the expected benefit and impact for the industry being, of course, those of binder jet. So high throughput, much faster build rate than laser powder bed fusion, low operating costs, and adapt for very complex parts. So thanks to a big team, it was my pleasure to be with you today. I thank you very much. I hope you have an excellent day.
Thank you very much, Melissa, for giving us an overview of all these large-scale projects. Really helpful. May I ask all the presenters to come on screen? And I will invite the audience at this point to put questions in the chat line. And if you want to direct the questions to a particular presenter, please mention that. Otherwise, we will bring it forward to all. Bernie Dunker, the Associate Vice President, Interdisciplinary Research, will also come online right now in video, and he will be moderating the question and answer period from the audience. I'll take the opportunity, as I'm online right now, Bernie, to mention to all the speakers, everybody wants a part of this exciting activity. Everybody wants to share it. And we've heard Essam talk about repeatability, about speed. We've heard Mahalia talk about quality and efficiency, and Ali optimization and AI techniques related to optimization. I wonder if any of the speakers would talk about when we can all share this in a mass scale. What pieces of these are holding us back right now? We've heard about some major projects taking place, but much more mass scale production here. Everybody is interested in hearing which are the pieces that still need a bit more research or a bit more activity, or maybe it's materials. Could we get some comments on that? And then Bernie, if you would, there's a question already in the chat line, if you would monitor after.
Oh, here you go. All right. Thank you very much, Charming, for this nice question. Mass production in plastic area is happening right now with some new technologies offered with the European companies. But when it comes to metal additive manufacturing, one of the major issues is associated with quality assurance. We don't want to really do testing on each individual part printed by any of metal additive manufacturing technologies. We need to really certify parts as they are being built. And this is a very, in fact, a major area that need to be addressed. But this has brought a lot of opportunities because now people are thinking about advanced monitoring and quality assurance algorithms built in within the machine. Artificial intelligence becomes so important when it comes to quality assurance. And it is happening as I'm speaking. But my expectation is for metal additive manufacturing to really get to mass production, still we need 5 to 10 years to really come up with reliable platforms in terms of quality assurance and also in situ monitoring.
Thank you so much. I want to a response to that question before we move on to some of the questions that come through in the chat. Feel free to just jump in here, any of the panelists.
Yeah, I'd like to add one comment. So in addition to scalability of processes for metal AM and process robustness through monitoring and controls, I would say that material availability or the library of available materials is also still a challenge. And I believe Ali had touched upon that as well as Melissa in their presentations. And I wanted to highlight that the University of Waterloo has partnered on this thread with the NRC at their new site here in Mississauga. So we're very excited to explore that thread as well.
Of course, thrilled about the collaboration with NRC at Mississauga site. And Melissa, there was a question in the chat, I think it was asking tech projects in Ontario, and I know you told us about a number of exciting projects. Tell us which of those might be in Ontario or any others you'd like to highlight.
All of them are in Ontario and Quebec and Winnipeg. So, I mean, it's the location of the company that drives, you know, all the company comes from everywhere across the country, but the project may be driven from 5 different locations. So it's completely transparent for the players, the industry players.
Pan-Canadian and collaborative, fantastic.
Yes.
So we'll move on to another question. This is for Mahalia. How do you remove the support material generated during laser powder bed fusion, specifically for a curved or complex geometry? Okay, we're getting into some specifics now.
I was just typing the answer in the chat. I wasn't sure if that was going to be addressed. So this has been probably one of the most neglected aspects of the laser powder bed fusion process. And I think right now, some of the research that is looking at how do you optimize process parameters for support structures such that they can be manually removable is quite an active field. So although I don't have a straightforward answer, both Ali and Melissa, as well as Professor Toyserkhani, had mentioned active research in this space. So hopefully stay tuned. Maybe next year, this time, I'll have a good answer for that.
We'll have to organize another research session, a research talks session. Great, thank you. All right, the next question is directed to any panelist who wants to take a stab at it. how is critical surface quality and surface functionalization for AM? Are there technical challenges and therefore opportunities for collaboration? So what
Ali,
yeah, go ahead.
Okay, I actually just provide you with a very short answer, and I will ask other panelists to help me. Just to confirm what Professor Mahalia mentioned about support, there is a very interesting trend in R&D centers to print structures without support. We call it supportless structures. And this is one of the major activities at Essam. We are now printing some specific alloys, unfortunately I cannot disclose because of confidentiality, without any support. So we print them without support. That means we don't need to really remove any support. So that question becomes irrelevant if we would be able to develop a technology that can print structures without support. As per surface roughness, definitely it has a major effect on lifetime of metallic components. But again, there are many activities in research centers, including Essam, to develop specific research recipes to come up with surface roughness below 5 micron. And this is something that has been achieved, but there might be some, depending on application, we may need to have some post-processing like electroplating or electropolishing to support additively manufactured parts to finalize the surface roughness much better.
We have a minute or two if another panelist would like to jump in here and offer some thoughts on this question.
I should mention that on the other spectrum, for certain biomedical applications, you are interested in very high surface topography or surface roughnesses because cell attachment and proliferation happens on those types of surfaces. So studying how you can do surface functionalization in situ as you're printing is something that's very important. And it's a challenging problem because it is process specific and material specific. So this is a very, very interesting aspect that we're continuing to work on as well.
Okay, thank you. I've got an eye on the time now. Very much to the audience members for your questions and panelists for your responses. I'm going to turn it over now to Charmaine for some closing remarks.
Well, this is such an exciting field. It's such a pleasure to have you all here to update us on it. I think Bernie is right. We'll need an update. Essam, you said 5 to 10 years. We'll be able to have household products related to it. I am, we're already seeing some of the design capabilities as you try something out and you realize, wait a second, why don't we print something different that will allow A and B to happen instead, and then create a new design for a tool or a part or put it in. I've heard a lot about that activity from you, Essam, and from Mahalia from the lab. So it's not just going to transform how we create products, it's also going to transform the whole design of products as we move forward. So, we're all looking forward to seeing how this unfolds. I want to thank everybody, all of you, Essam, Mahalia, Ali, and Melissa, for taking the time to share this information with our community to bring us up to date on this very exciting part of manufacturing. I'd also like to thank the audience for being here with us today. We have a very large audience today. I hope that you enjoyed learning about and discussing these topics. And as always, we welcome your feedback and suggestions for future topics. Please don't hesitate to send suggestions to us. And we also look forward to seeing you at our next research talks. Thank you again, Essam and Mahalia and Ali and Melissa. Really interesting presentations today. Thank you for bringing us up to date on additive manufacturing. And again, fabulous talks Thanks very much, everyone, for being here today. Bye, everyone.